Exponential functions are going to be are special because of the way that they grow. So increasing exponential functions are always going to grow at a rate that's proportional to their size. And decreasing exponential functions are always going to decrease at a rate that's proportional to their size. And so what that's going to mean is that we are in a given time period, we're always going to either gain the same percentage of our function, or we'll lose the same percentage of our function. Okay. Another way of saying this is that the time it takes for the function to either double or be halved will be the same no matter what time we start looking at it at. In the case that our population is growing, this will be called the doubling time. And if our function is decreasing, this is going to be called the half-life. For example, if we are investing money in the stock market, we can expect that no matter how much we put in, that the amount of money we have will double within 7 years. Okay, so let's take a look at just to compare and contrast the function 2 to the x, which is exponential with base 2, with the linear function g of x equals 2 times x. We see in the exponential function, as x grows by 1 each time, we are doubling how we are doubling our output. In contrast, if we look at a linear function, each time our time increases by 1, we are adding 2. All right. So each time our x goes up by 1, we have doubled the value of our function in the exponential case. And so we will say that the doubling time here is equal to 1. Great. Okay. So we're going to just take a quick look at the sort of general shape of the graphs for b to the x, both in the case where b is greater than 1 and in the case where b is less than 1, but more than 0. So the function f of x equals b to the x. In the general graph of this is going to have this kind of shape. The domain is going to be all real numbers, -infinity to infinity. Its range is going to be 0 to infinity. The y-intercept is f at 0. So that's b to the 0, and that's equal to 1. So all of these functions, no matter what our base is, are all going to go through the point 0, 1 as our y-intercept. Because their range is 0 to infinity, there is no x-intercept. We never cross the x-axis. These functions don't have any breaks or jumps, so they are continuous. We are not going to, they are defined for all real numbers. So we are going to say that they have no vertical lines that they're getting close to. Okay. And we'll talk about these asymptotes, which is a feature of a graph, a little bit more later on. They do have a horizontal line that they get close to. This is called a horizontal asymptote, and it's the line y equals 0. So we can see here that this blue curve is going to get very close to this yellow line along the x-axis, which is the line y equals 0. And so we would say, yes, this has what's called a horizontal line, a line that the function values get arbitrarily close to. This function is always rising, and so we're going to say it's increasing. And it's certainly invertible. If we draw it in horizontal lines, we see that we only hit the graph once. There's no repetition of y values. So this will have an inverse. And we'll be studying the inverse later this week. So this is our general shape when our base b is greater than 1. Okay. Next, let's take a look at the shape when our base is less than 1, but more than 0. So this is going to be where b is less than 1. So an example of this would be b to the x is 1/2 to the x. Okay. So here our base is equal to 1/2. At each time step, we're taking half as much as we had before. And so the shape of our graph this time is going to be decreasing. We can also see this in by rewriting our base inside as in this case 2 to the negative 1 to the x. So this is 2 to the negative x. That means we're taking a graph where the base is greater than 1, and we're reflecting it across the y-axis. So these guys are going to be decreasing functions, getting closer and closer and closer to 0. This is going to have the same y-intercept of 0, 1. Its domain is going to be the same, negative infinity to infinity. Its range is 0 to infinity. B to the 0 is always going to be equal to 1. This is our y-intercept. We are not going to see any jumps or breaks in our graph, so it's continuous. It's the way we say that. There are no vertical lines that we get really close to. But there is this horizontal one, y equals 0. Okay. This time our graph is decreasing. It's getting smaller over time. And it's still invertible. If we think about whether or not any y values are repeated, we see that there's no repetition of y values because it's always going down. Okay. So this is our general shape. There are a couple of easy points for us to identify on these graphs. The value at 1 is equal to b to the 1, or just b. The value here, again, at 1 is going to be b to the 1, or b. Okay, so what I'd like you to do next is take a look. Here we have a couple of graphs. We have exponentials with base 2, 4, and 1/3. And I'd like you to take a moment looking this over to try and figure out which one is which. So please pause the video, try and decide which is 2 to the x, which is 4 to the x, and which is 1/3 to the x. Okay, so the easiest one to figure out here is 1/3 to the x. We see here that our base is equal to 1/3. So this is going to be decreasing. And so the only decreasing function we see here is this green curve, h of x is going to be 1/3 to the x. Alrighty, great. And now we have to figure out which one is 2 to the x and which is 4 to the x. So it's either the blue or the red. So one easy way to compare is to think about which one will have larger outputs. So we could try plugging in values. So we could look, for example, at f at 1 and g at 1. You might have tried this. F at 1 is equal to 2 to the 1, which is 2. G at 1 is 4 to the 1, which is 4. And so we see that at 1, we've got 2 and 4 as our outputs. And so f of x equals 2 to the x is the red curve. And g of x equals 4 to the x is our blue curve. One thing I'd like you to notice here is how these guys compare in size. When x is bigger than 0, 4 to the x is going to be bigger than 2 to the x. Notice when x is less than 0, which function has bigger values is going to swap. The red curve now has smaller values, and the blue one has, sorry, I said that backwards. The red curve has bigger values, the blue curve has smaller values. So when x is less than 0, then we'll see that 2 to the x is bigger than 4 to the x. So what we will see is that if you have a bigger base, when we take powers that are positive, we have bigger outputs. When we have negative powers, we're getting closer to 0 faster. Okay, so they're going to move at a quicker rate. Okay. All right. So next up, we're going to take a look at a couple of examples. So here we have some graphs of functions. We can see in the first case that our base was greater than 1 because we're increasing. And in the second case that our base is less than 1 because we're decreasing. And what we'd like to do is try and figure out what exponential function we are looking at. So we're told that our function has this form, f of x equals b to the x, and we'd like to match it. So take a moment, pause the video, and give it a try. Alrighty, so let's take a look at this. So we know here that f of x is equal to b to the x, and we're given a point on this graph. We know that f at 2, which is b squared, is going to be equal to 25. And so by taking square roots of both sides, we get that b must be equal to 5. Because our bases have to be positive, we can only take the positive square root here. So here we see f of x is equal to 5 to the x in this first example. In our second example, we have f of x equals b to the x. And we can evaluate at 3. We have b cubed is equal to 1/8. And so our goal is going to be to say, what is this b? So b cubed is equal to 1/8. So to find b, we can just take the third root of both sides. So b is going to be the 1/3 root of 1/8, or 1/8 to the 1/3 power. And we can take the simplifications that we've seen before, that if you have a fraction to an exponent, that we can apply that exponent to the top and bottom separately. 1 to any power is just 1, and then the cube root of 8 is equal to 2. And so we see that our function here is f of x equals 1/2 to the x. Awesome.